Alright, we're done with appetite regulation. Now we're going to hit on the far more board-tested concept of thirst and fluid regulation. This is a majorly important crossover topic that straddles endocrine, renal, and cardiovascular physiology, but we're mostly going to focus on the endocrine side of things. First, let me ask you, why do people get thirsty? It's not a trick question or some philosophical point I'm trying to prove to you. The answer is to let them know that they need to drink water. Simple. And when do we need to increase our water intake? Now, the answer to this question is a little bit trickier. The most obvious answer is when we're dehydrated, or more accurately, when we're hypovolemic. This is mediated by angiotensin II and arterial baroreceptors that communicate with the more primitive areas of the brain to let it know, hey man, we need más agua. The less obvious reason to drink more water is that our blood's too hypertonic. Think about it. Water isn't a replacement for the fluid in our bodies like the serum. Normal saline is. Water is extremely hypotonic, meaning that the other function of drinking fresh water is to dilute the blood. Osmoreceptors in the central nervous system communicate with the hypothalamus to tell it the sodium concentration is getting too high. So now the central nervous system's aware of the fact that it needs water, it's going to do two things. First, it communicates with the limbic system in the cortex to actually get you to drink water, which both increases the body's fluid volume and decreases its sodium concentration. At the same time, the hypothalamus releases antidiuretic hormone via the posterior pituitary, which works on the kidneys to achieve the exact same goals as drinking water. But let me be clear, there's a lot of systems in place to help fight hypovolemia and hypotension. ADH's most important and unique role is to decrease the sodium concentration in the blood. To understand how this works, it's helpful to contrast it with another important hormone, aldosterone. Both aldosterone and ADH are important when it comes to fluid retention and maintaining blood pressure, so it's particularly important not to mix them up. First, while aldosterone stimulates the retention of saline solution via active reuptake of sodium and the resulting osmosis, ADH leads to the retention of free water. It does this by stimulating the insertion of sequestered aquaporins into the apical membrane, allowing water to passively osmose into the interstitium and eventually the capillaries. As you can see, ADH really does pretty much the same thing as just going out and drinking water. But wait a minute, says you, why does inserting pores willy-nilly into the membrane mean that water is necessarily going to osmose out of the renal tubule? Doesn't it depend on the osmotic gradient? Remember from renal, the renal interstitium, especially in the medulla, is extremely salty. Remember all that countercurrent gradient stuff? It's okay, I won't remember. I won't make you think about it right now. But the bottom line is, if you punch holes in the renal tubule, water is always going to come rushing out to dilute the salty renal interstitium, because that's where the osmotic gradient is. Aldosterone does a couple other important things at the kidney, including potassium and hydrogen ion excretion, but the important contrast between ADH and aldosterone is that though both of them cause fluid retention, the different composition of fluids means that ADH is capable of modulating the osmolality of the blood, whereas aldosterone isn't to any significant degree. So to answer the question that led us to this slide in the first place, what is the primary purpose of ADH? It's the very thing that makes it unique, its ability to modulate the osmolality of the blood. If you need to brush up on your renal physiology, don't feel bad, it's complicated stuff, but make sure to check out our renal chapter for more details. So to sum it up, antidiuretic hormone responds to hypovolemia and hyperosmolar blood by causing free water retention, which decreases the osmolality of the blood, and it does so via V2 receptors on the distal tubules and collecting ducts. In response to low blood pressure, it additionally causes arteriolar constriction via V1 receptors. This is what gives it the alternate name vasopressin. Pause this video and take a quick look at the diagram if you need to, because after you do, you're in for a flash quiz. Here's a fill-in-the-blank question for you. Antidiuretic hormone's main effect on the renal tubular epithelium is to increase surface expression of blank, which causes water to move into the blank via osmosis. Go ahead and pause the video if you need a moment to think. And the answer is, antidiuretic hormone's main effect on the renal tubular epithelium is to increase surface expression of aquaporins, which causes water to move into the renal interstitium via osmosis. For the second blank, I also would have accepted renal capillaries, because that's where the water eventually ends up. So now that we've covered appetite and thirst regulation, let's move back into the world of the pituitary hormones with one of the major players in endocrinology, the hypothalamic pituitary adrenal axes. Since I'm sadistic and horrible, I thought I'd start with this, the diagram from hell. The bad news is all of this is fair game, and you would not be wrong to try to memorize it all. But the good news is we can work through this so that it's less about memorizing the whole shenanigans and more about keeping it simple and internalizing a few patterns. I'll point out the most important nuggets along the way so you learn the high-yield stuff before trying to cram every last bit of trivia into your brains. First thing you gotta know, what basic molecule makes all steroids possible? The answer is cholesterol, the precursor molecule to every one of these bad boys. Its conversion to pregnenolone is the rate-limiting step, the one that's controlled by ACTH. Once ACTH allows entry into the steroid synthesis pathway, the magic can begin. Quick, what are the 3 layers of the adrenal cortex in order from outside to inside? Go! Okay, time's up. You should really know this one. The 3 layers, the glomerulosa, fasciculata, and reticularis, synthesize different steroids, and it's all dependent on a set of what I call the gateway enzymes. Let me show you what I mean. The glomerulosa layer has all the right enzymes to synthesize aldosterone, but it lacks the 17-alpha hydroxylase required to synthesize cortisol. The fasciculata layer's hydroxylase works fast enough to route steroid production pretty much exclusively to cholesterol, but it lacks the 1720 lyase that the reticularis layer uses to synthesize DHEA, androstenedione, and to some extent testosterone. FYI, the main steroids synthesized in the zona reticularis are DHEA and androstenedione. Testosterone, which is a much more potent androgen, is really in the minority. Now, here's the bare minimum of what you need to know. 1. Cholesterol is converted from pregnenolone to progesterone, and both pregnenolone and progesterone need to be 17-alpha hydroxylated in order to enter the cortisol pathway. 2. To get closer to the end products aldosterone and cortisol, the first 2 enzymes are the same, and yes, you do need to know their names. The first is 21-hydroxylase, the second is 11-beta-hydroxylase. The alpha and beta aren't really so important, but the numbers very much are. 3. The pathways towards aldosterone and cortisol synthesis have a bunch of intermediates that all sound like cortico something. But here's the weird thing. They all have mineralocorticoid and not glucocorticoid activity. I'll say it again. If it sounds like the word cortisol, but isn't, be it corticosterone or 11-cortico whatever, it does not act like cortisol. It acts like a weak aldosterone. Finally, and this is an old point, while ACTH may control entry into the steroid synthesis pathway, angiotensin II is required for the final step of aldosterone synthesis. Thus, it's controlled independently from the hypothalamic pituitary adrenal axis. Got all that? I get you. Even the bare minimum seems like a lot, but we'll work through a clinical example together, and I think it'll make a whole lot more sense then. Congenital adrenal hyperplasia is the main way in which you'll be tested on steroidogenesis. It involves a partial deficiency in one of the steps used to synthesize cortisol. And since cortisol is the main hormone that feedback suppresses CRH and ACTH, low cortisol is going to cause a significant bump in ACTH. This not only routes more cholesterol into the steroid synthesis pathway, increased ACTH also causes a global proliferation in all cells of the adrenal cortex in a misguided attempt to get them to crank out more steroids. Like I said, the cortisol deficiency is only partial and isn't usually a big deal. But depending on the enzyme that gets knocked out, there can be clinically significant derangements of either the mineralocorticoids or the androgens. So first off, let's recap what they do, starting with aldosterone. What's its effect on blood pressure? What about potassium? Aldosterone increases blood pressure by causing salt and fluid retention, but sacrifices potassium for sodium via the sodium-potassium pump. What about androgens? Alright, this is an easier one. In a fetus, they cause the development of male external genitalia. In adolescence, they cause the development of male secondary sexual characteristics. So take one last look at this diagram and let's try to work this out from memory. Think you can handle it? I hope so, because we are going! First up, what would you phenotypically expect from the most common form of CAH, 21-hydroxylase deficiency? Pause the video for a moment and think back to the diagram. Can you remember which pathways are inhibited? A 21-hydroxylase deficiency shuts down synthesis of mineralocorticoids and cortisol, leaving behind only the sex steroid pathway. And because the stupid pituitary assumes that if there's not enough cortisol, the whole adrenal gland needs a kick in the pants, that means there's going to be a serious excess of adrenal androgens. So how do the parameters listed in the table below change? Aldosterone, like we said, is responsible for increasing blood pressure but sacrificing potassium. But since the mineralocorticoid pathway is shut down, we'd expect to see the opposite: decreased blood pressure and increased potassium. We'd expect the increased androgens to cause increased development of the male external organs, but what we actually see is actually a lot more noticeable in females. The excess androgens give the developing lady parts mixed signals, causing a range of virilized phenotypes, ranging from clitoromegaly to vaginal underdevelopment. You actually don't usually see any sexual side effects in infant boys, though they often undergo precocious puberty. As it turns out, though, genital ambiguity in infancy may actually be a good thing. It at least warns you that there's a problem going on. With girls, you notice the weird genitals and say, oh my god, something's wrong, and usually the problem gets taken care of. What sometimes happens to boys is that they get sent home because everything looks okay on the outside. Meanwhile, their aldosterone deficiency causes them to dehydrate like crazy, and the next time they're brought in, it's to the ICU, because babies can't tell you they're thirsty. In fact, the only clinical sign that's routinely present is severe vomiting. So here's a summary of what goes on in 21-hydroxylase deficiency. Now pause the video and see if you can do the same for an 11-beta-hydroxylase deficiency. So the first step is to figure out what pathways are closed off. Remember important pathway number 2, the first two enzymes that divert the progesterones down the aldo and cortisol pathways are 21-hydroxylase and 11-beta-hydroxylase. So an 11-beta-hydroxylase simply shuts down the production of aldo and cortisol just one step later. Sounds like it causes the same problems, right? Wrong! The virilizing effects on girls are similar because the sex steroid pathway is still the only one that goes completely untouched. But harken back to important fact number 3. Once you go down the aldocortisol pathways past progesterone, you have a whole bunch of cortico-sounding intermediates that all have weak mineralocorticoid activity, no matter which side of the pathway they're on. And 11-beta, unlike 21-hydroxylase, is downstream of the first cortico-intermediates. But Arjun, you ask, aren't they just weak mineralocorticoids? Verily they are, says I, but remember, with a lack of cortisol, the pituitary has literally no idea that the adrenals are doing anything at all, and sends ACTH to make the adrenals work double time. That double time production of even a weak mineralocorticoid is usually enough to cause mineralocorticoid excess, meaning that the blood pressure will be increased and potassium will be decreased, as you can see in the table below. There's one more important form of CAH that I'm going to have you do on your own, this time in the form of a flash quiz. Your question is, how would you expect the following to change in 17-alpha hydroxylase deficiency? Mineralocorticoid activity and androgen activity. These are essentially the same parameters as before, just like we did earlier. Pause the video and attempt to work this out step by step. Since 17-alpha is the gateway hormone that allows synthesis of the glucocorticoids and is thus also required for the synthesis of sex steroids, both cortisol and sex steroids will be diminished, and you'll have a lot of aldosterone. We're not even talking about that wimpy 11-cortico stuff. This is the real deal. As a result, blood pressure is going to skyrocket, potassium will drop, and it'll actually be the boys that end up with the ambiguous genitals because testosterone is required to properly develop the male genitals. Girls only experience the sexual effects of 17-alpha deficiency at puberty because they may not be able to synthesize the requisite estrogen to develop secondary sex characteristics. Hopefully this all makes a little more sense now. It's a little tough to remember all of steroidogenesis, but I think working through examples makes it more memorable. So, I think I successfully made the case that sex steroids are pretty essential to normal development. And it doesn't take a genius to realize that they're pretty important in maintaining certain functions in adults as well. Difficult as it may be, can you think of any times that sex steroids are pretty unhelpful, or even downright harmful? To answer this question, remember that sex steroids, like many steroids, are responsible for the growth and development of certain tissues. Take breast tissue, for example. Now, there's nothing wrong with the growth of breast tissue under normal circumstances, but the problem arises when certain breast cancers happen to be estrogen responsive as well. The same also goes for ovaries, so we employ certain drugs to prevent inappropriate cell growth. The aromatase inhibitors, anastrozole and exemestane, prevent the synthesis of estrogens from their androgen precursors. Estrogens can also be blocked on the receptor end with receptor blockers like tamoxifen and raloxifene. So what's the male equivalent? I'll give you a hint. Unlike breasts, this one isn't visible from the surface. Bad prostate growth comes in a couple different flavors, benign prostatic hypertrophy being the lesser of two evils. Since prostate growth is mostly dependent on the more powerful androgen DHT, the 5-alpha reductase blocker finasteride can help this issue by inhibiting 5-alpha reductase, shutting down production of DHT. Unfortunately, remember the weaker androgens testosterone and androstenedione do have some effect on prostate growth. So if you've got the really bad prostate news, namely prostate cancer, you're going to want to block all three of them with an androgen receptor blocker, like flutamide. You'll learn more about this in Repro, but for now we're going to focus on cortisol, one of the most complex and important hormones for step 1.